Welcome to episode 8 of our Python Developer Bootcamp. In this episode, we will explore a fundamental aspect of software development that often separates novice programmers from seasoned professionals. In this installment, we'll delve into the critical world of error handling and debugging. These are essential skills that every developer must master to ensure their code is not just functional, but also reliable and maintainable. Writing code that merely functions is not enough. We strive to craft code that is resilient, robust, and capable of gracefully handling unexpected situations. This means anticipating potential issues and designing solutions that can adapt to a variety of scenarios. Errors are an inevitable part of the software development process. No matter how experienced you are, mistakes will happen and unforeseen issues will arise. They can arise from various sources: invalid user input, unavailable resources, or even unforeseen logic errors within our code. Each of these errors presents a unique challenge that requires a thoughtful approach to resolve. If not handled properly, these errors can lead to program crashes, data corruption, or security vulnerabilities. Such issues can have serious consequences, from minor inconveniences to major system failures. This is where the concepts of exception handling and debugging come into play. Exception handling allows us to manage errors gracefully, ensuring that our programs can recover from unexpected events without crashing. Exception handling allows our programs to anticipate and respond to errors in a controlled manner, preventing abrupt terminations. It involves writing code that can detect and respond to errors, providing alternative solutions or informative messages to the user. Debugging, on the other hand, equips us with the tools to identify and rectify the root causes of these errors. It involves systematically examining our code to find and fix bugs, ensuring that our programs run smoothly. By mastering these techniques, you'll transform from a Python programmer into a Python architect, capable of designing systems that are not only functional, but also robust and scalable. Building applications that are not only functional, but also reliable and maintainable is the hallmark of a true software engineer. So let's dive in and start mastering the art of writing robust code. Python provides a powerful mechanism for handling runtime errors, the try-except block. This construct allows you to try executing a block of code that might raise an exception and catch that exception if it occurs, preventing the program from crashing. The syntax of a try-except block is straightforward. First, the code that could potentially raise an exception is placed within the try block. Following the try block, one or more except blocks are defined, each designed to handle a specific type of exception. For example, try result =10 divided by 0 hash. This will raise a zero division error except zero division error. In this example, the code attempts to divide 10 by 0, which would normally result in a zero division error. However, the try-except block intercepts this error, and the code within the except zero division error block is executed, printing an error message to the console. The try-except block acts as a safety net, allowing your program to gracefully handle unexpected situations and continue running smoothly. Python provides a rich hierarchy of built-in exception classes, each representing a specific error type. These exceptions help developers identify and handle errors more effectively. Understanding these exceptions is crucial for writing effective error handling code. By knowing what each exception signifies, you can write more robust and error-resistant programs. Here are some common exception types you'll encounter. Type error raised. When an operation is performed on an object of an inappropriate type, such as trying to add a string to an integer. This often happens when data types are mixed inappropriately. Value error, raised when an operation receives an argument of the correct type but an inappropriate value, such as trying to convert a string that doesn't represent a number to an integer. This is common in data validation scenarios. Index error raised when trying to access an index that is out of range for a list or tuple. This can occur when iterating over lists without proper bounds checking. Key error raised when trying to access a key that doesn't exist in a dictionary. This is often seen when working with dictionaries and missing keys. I/O error, raised when an input-output operation fails, such as trying to open a file that doesn't exist. This can happen due to file permissions or missing files. Import error, raised when an import statement fails to find or load a module. This is common when dependencies are not installed or paths are incorrect. Each exception type carries specific information about the error that occurred. This information is invaluable for debugging and improving code quality. This information can be accessed within the except block, allowing you to tailor your error handling logic. By leveraging these details, you can create more resilient and user-friendly applications. While Python's built-in exceptions cover a wide range of errors, there are times when you'll need to raise exceptions manually within your own code. This is particularly useful for signaling errors specific to your application's logic. The raise statement allows you to raise an exception explicitly. You can raise a built-in exception class or create your own custom exception classes. For example, def calculate discount price, discount_percentage. If discount_percentage is less than 0 or greater than 100, raise value error discount percentage must be between 0 and 100. In this example, the calculate_discount function checks if the provided discount_percentage is within the valid range. If not, it raises a value error with a descriptive message. By raising exceptions in your code, you can enforce constraints, validate input, and signal errors in a way that is both informative and consistent with Python's exception handling model. Section 5. Ensuring clean execution, the finally clause. In addition to, and, the block can also include an optional clause. The code within the block is always executed, regardless of whether an exception occurred or was handled. This is particularly useful for releasing resources that might have been acquired within the block, such as closing files or database connections. Python try. In this example, the block ensures that the file is closed properly, even if an error occurs while opening or processing the file. This helps prevent resource leaks and ensures that your program cleans up after itself. Section 6. Crafting clarity, custom exception classes. As your Python projects grow in complexity, you might encounter situations where the built-in exception classes don't fully capture the nuances of your application's errors. These built-in exceptions, while useful, can sometimes be too generic, making it difficult to pinpoint the exact issue. In such cases, you can create custom exception classes to represent specific error conditions. This not only helps in identifying the error more accurately, but also makes your code more readable and maintainable. Custom exceptions inherit from the base class or one of its subclasses. This means you can leverage the existing exception hierarchy while adding your own custom logic. By defining your own exception classes, you can provide more descriptive error messages, include additional error-specific attributes, and create a more organized and informative error handling system. For example, you can add attributes that store additional information about the error, such as error codes or invalid values. Class invalid input error exception. Media group. Screen recording of Python code with custom exception class and descriptive error messages at stock at distribute_equally. Custom exception for invalid user input. Def self message input message self.input_value =input_value hash. Example usage: def process input value, if not instance value int, raise invalid input error, input must be an integer. Value, hash process. The input here is a custom exception class that stores the invalid input value. This makes it easier to debug and understand what went wrong. This allows you to provide more context in your error messages and handle different error scenarios with greater precision. Custom exceptions can be a powerful tool in your error handling arsenal, making your code more robust and easier to troubleshoot. Section 7. Debugging 101. The power of print statements. Debugging is the art of identifying and fixing errors in your code. While it might seem daunting at first, it's an essential skill for any programmer. One of the simplest yet most effective debugging techniques is the strategic use of statements. By inserting statements at various points in your code, you can inspect the values of variables, track the flow of execution, and pinpoint the source of errors. Let me give you an example. Python def, calculate average, numbers, print numbers hash debug, check input, total =sum numbers, print total hash debug, check intermediate value average total, len numbers, return average. In this example, the statements act like breadcrumbs, revealing the values of and at different stages of the function. This can help you identify if the input is correct, if calculations are performed as expected, and ultimately, where the error might lie. Section 8. Unveiling object secrets, DR, and type. Python provides several built-in functions that can aid in debugging by providing insights into objects and their properties. Two particularly useful functions are and. The function returns a list of all attributes and methods available for a given object. This is invaluable for exploring objects, understanding their capabilities, and identifying potential issues. Here's a quick look Python. My underscore list =123 print, dir my append clear. The function returns the type of an object. This is helpful for verifying if a variable holds the expected type of data and can help diagnose exceptions. For instance, Python x =10 print type x hash output. By strategically using and, you can gain a deeper understanding of your objects, uncover potential issues related to object types, and streamline your debugging process. Section 9. Mastering the debugger. Stepping through your code with PDB. While statements and built-in functions are helpful, Python offers an even more powerful tool for debugging, the Python debugger, or the module allows you to step through your code line by line, inspect variables, set breakpoints, and gain granular control over the execution flow. To use, insert within your code where you want the debugger to pause execution. Once the debugger is activated, you can use commands like next, step into, continue, and print to navigate and inspect your code. For example, Python import pdb def my function, media group, screen recording of a Python script with inserted and demonstrating commands, screen recording of a sample function in Python with commands, awkstock, distribute equally. The Python debugger might seem intimidating at first, but mastering its commands can significantly enhance your debugging efficiency. It allows you to pinpoint the exact location of errors and understand the state of your program at any given moment. Section 10. Towards bug-free code practice makes perfect. Congratulations on reaching the end of episode 8. You've now been introduced to the fundamental concepts of error handling and debugging in Python. Remember that writing robust and bug-resistant code is an iterative process. Embrace the block as your shield against runtime errors. Familiarize yourself with Python's diverse exception landscape, and don't hesitate to craft your own custom exceptions for enhanced clarity. Make statements your allies in the debugging battlefield. Leverage the introspective power of and dare to venture into the depths of the Python debugger. Most importantly, approach each bug as a learning opportunity